All right, so we are week 17, day 3, second week of learning machine learning models, AI, LLMs, all that jazz. Looks like this week we've done a couple of lectures on training our model, correct? Like last week we did kind of behind the scenes of what builds out our machine learning models. And then this week we're learning how to actually train them. Um, Still haven't gotten much past that. We've learned about the loss and optimization and all that. So after last class, this should be kind of familiar, or at least Monday's class, one of those, where we ended up with our binary model, and we have all the training features in here with our dropout, and when we run, let's see, further training on it, we use like oh gosh, we use some sort of loss feature here that I don't have pulled up right now, but this is kind of a model you've come to expect and see, right? We put in your tensor of features, and then it's supposed to produce basically a yes or no output, right? It's a number between 0 and 1, and whichever way it leans, in the range there between like 0 to 0.5 or 0.5 and up, is giving you that yes or no answer. So we did water potability. We wanted to see, is it potable? Yes or no. So that's pretty awesome. But there's so many more things we can do with machine learning, and I don't want to always have to prompt for a yes, no answer. So today we're going to learn about what if we want to, let's say, give a whole bunch of features to it and instead return back a value instead of a yes or no. So that sounds a little abstract, but like weather prediction. What if I want to give all the, I guess, weather variables like temperature, humidity, dew point, all that kind of stuff, and I want it to give back a forecast of, sunny, rainy, snowy, some options there. So right now with our binary model, we can't do that. We can only say, is it going to snow? Yes or no. But I want to return back, what is it going to do given all these variables? So today we're looking at what's called multi-classification models. So we're going to be expanding on this binary model where we just get a yes or no answer. And we're going to categorize into more than two classes, which is the yes or the no. So if you have the README open, we're just going to kind of step through kind of the differences between a binary classification and then our multi-class classification. So let me pull up our image here of doing this. So we can see, kind of looks familiar. Looks like we've been learning last week where you have your features that are the input into this model. Goes through all these hidden layers, of course, doing all that magic behind the scenes. And then has an activation layer, just like we had with the binary. And then shoots out now, instead of two outputs, like a yes or no, or sorry, it's a 1 with the binary, but it's a value between 0 to 1. This one has multiple output percentages. So what this is going to do is it's going to take all these classes that you have decided you're going to decide between, or that's decided, you're going to figure out the probability or likelihood that it fits in that class. So if we're giving, it sounds kind of weird, if we're giving like all of our weather variables into this model, let's say this box up here is rainy, this one's sunny, this one's snowy, and this one's foggy. So the output is actually going to give us percentages of how likely it's going to be that weather. And these all together should equal up to 100% or 1, because it's going to be a float, a decimal. So it'll output something like, well, given those values you gave me for our features, I think it's going to be 0.2 and whatever this was, I forgot already, rainy, 0.5 and sunny, 0 in snowy, and then math, what did I, 5.2? So 0.3 in whatever this one was down here. So when it gives all those outputs, because we want this to tell us, it's guess. What is the weather going to do that day? So instead of, just working with all these different outputs, we're going to take the largest value of these outputs as our prediction from this model. So we're going to go through it and have an example here that will hopefully make a little more sense. I remember last class we're like, don't really understand how we can use this in real world applications, right? All this machine learning stuff. I use the weather one a lot, but I just did like a Google search and I'm like, what can we use multi-classification models for? And we could do something, and it had some pretty cool ideas, like maybe disease diagnosis. If we pass in a series of x-rays as our features, and then our output would be diagnosing between like pneumonia, COVID, or normal lung function. It'd give us that kind of classification percentage between those just based on the x-rays. So you could do something like that. You can pass in image recognition is a big one. So if you pass in a picture, this multi-classification will go ahead and, assign it to a label of like dog, cat, horse, bird, something like that. So just a couple examples of how you could use this in real life. And then actually our example we'll work through today is also pretty real life as well. So first thing we're going to do is I'm going to pull up the code of what our multi-classification model is going to look like and pop it right underneath our binary model. And we're going to kind of compare the differences there because there's several big differences between the two. Not all will be visible right here just yet. But right off the bat, I don't know how I can put it up on the side like you can. I don't think that's going to do what I wanted to do. I was hoping I can have y'all look at this easier and kind of tell me any differences you notice between these two.
You have softmax instead of sigmoid.
Yep. I think, Jonathan, you said that right. And then Mike, did you see something else or you?
I was asking, are you able to do a split screen and then you could run from one or the other? Like, you know how you right click and then you split right? Okay, or that.
Oh, let's see. I'm trying to, yep. Okay. Let's do that. It'll be a little confusing, but there. So we're comparing, this is our binary, here's our multi. And Jonathan, that was one of the biggest differences between these two is our activation layer here. In our binary, we use sigmoid. In our multi-classification, we're going to use softmax. And this is used because in the binary, it expects one output. But in this multi-classification one, you're going to get several outputs based on how many labels you've chosen to select for your classification. So we can't just produce one number. We're going to have a whole bunch of values, and this softmax is going to take them all, and they're all probabilities, and this is going to make sure that each of those probabilities equals to 1. So it's going to go through those probabilities and squish them down if it has to, just to make sure that it's another kind of like standardization here, where it's going to make sure that all those probabilities equal to 1 at the end. So that way we can have a nice readable output percentage-wise. So that is definitely one of the biggest differences between our multi-classification and our binary. Let's see. Anything else stick out here that we can see? To me, I don't see anything different. We're still using the same sort of dropout here in between our linear layers. We use this ReLU. You guys touched on that last time to help with more complex processing. And again, we're using that softmax instead of sigmoid for our activation layer. Cool. So let's start with that. Oh, I just deleted it. That's okay. Geez, I can't. We're gonna pull up that model again, and we are actually going to get hands-on with the student performance CSV and kind of work through how we're going to process data to pass into this model, and then how we're going to train this model, because that's where some of the other differences are going to pop up as well. So here is our multi-model. Again, this is just in our README for today. You can go ahead and copy it. Just for ease of like readability, I'm going to put my pre-processing before the model just because I like to. But we're going to go ahead and pre-process our data for this model. So let's take a look at it. We got this student performance CSV. And let's see, this is going to have a whole bunch of different columns up here. Our target is going to be this grade class, which, as we can see here, grade class is not just 0 or 1. It's a whole bunch of different values. Basically, this is their GPA. This is the grade that these students have achieved. So its GPA ranges from 0 to 4.0. So our goal is we want to be able to pass in this information, and guess what their grade would be based on all these other parameters. So first things first, when we pre-process, what do we have to do first in order to pre-process our data? Does anybody remember? What libraries are we using? Let's start with that.
Pandas.
Yes, we will import pandas. We love pandas. As we do. Okay. What else do we use? There's another big one. Nope. Started with SK.
sklearn.
Yes, there we go. Okay, so we're going to import sklearn. And from there specifically, we're picking out model selection, because that is where we're going to do the split. There's a few different things, and you can, in whatever order, import. No, from. Choose from sklearn. We're going to import the train test split. This is what we're doing to split up our data into the training and testing data sets. Another one we're using from sklearn is we were going to do this pre-processing, and we're going to import our standard scaler. It's going to make sure all the data is within a certain scaled range so that we don't have any crazy deviations. And then these are just what we're going to need for our tensors, and everything else is we're going to import from Torch utils that data. I'm going to import tensor, and I think these should all be on that data, working with data class that we had. There should be a code snippet there that might have all these that you'll be importing. But this is what we will need for our pre-processing, because we're going to scale it. We're going to import pandas because we're going to do, let's see, several things first. We'll get there. And then we're going to split it after we do things with pandas, scale it, and then split it, and then we're going to load it into our tensors. Okay, so first things first, if I want to work with this CSV, what do I have to do with it?
fill in anything that's missing, so you don't have like holes in your data, right?
Yeah, we could do that. But first, before we do that, we need to pull it in here first. We're going to read our CSV first. So we're going to pull all data. And this is where we're using the pandas because it makes it a nice, pretty, spreadsheet looking like thing. We're going to read CSV. And it's going to be the student performance CSV. Okay, so here we're loading our data set ready to be worked with. Do you remember the code for finding all the null values or even seeing if there's null values? I don't either. I'm looking back.
You're talking about the data.isNull.sum, like the exploration piece?
Yeah, like if we want to see if there's even any null data in here to work with. So yeah, that would be it. So what we're doing, is it a print or?
Yeah, what I have in my notes is print, and then inside print it would be, I think, oh yeah, the name of your, so all data dot is null, and call that function dot sum, so it'll grab a number of how many are in there.
Okay. Let's see. So let's run this and see. All right, looks great. Nothing has null values. So this data set is amazing. We don't
That
have to
means
deal with.
we don't have to do the fill in a then.
Yep,
Okay.
cool. So that's a good thing to check though, for sure, because it will skew our results depending on, I would just throw out the null ones because I like to do that. That's just me. But so we're good. We checked it. We don't have any null values. So now we can move on to targeting what data we want for training and using. What we want to look at our features and figure out, do we need all these for our features? Can we work with a smaller subset of data? Can we drop anything? Because remember, we can drop columns if it's not useful.
I don't know what gender and ethnicity have anything to do with it.
I mean, it might.
If we're getting political,
Yeah. I mean, everybody's background could affect their GPA. I suppose that's part of the machine learning thing, is to see if it could. I'm leaning more towards maybe student ID.
Oh, yeah.
I don't think we need to know their ID. I don't think that has any impact on what grade they earn whatsoever. So I'm just probably going to clean up this column here, student ID, but the rest of it, I mean, theoretically could possibly have an impact on their grade. We don't know, but I'd like to see. So I'm going to throw the rest of it in there. Okay, so I want to drop student ID. How do I do that? Let's give it a variable first. Let's assign, we're going to say our new data here is going to be, it's very, very intuitive how to drop, maybe. I'm going to target my all data. And I want to drop. So I'm going to drop something from it. What should I put in this drop? Does anybody remember how we targeted what we wanted to drop from here?
Name, so it'd be student ID.
Yes. Okay. Was that all we needed to put in here?
I still don't understand why, but the axis, AXIS, is its own too.
Okay, yes. So if we just gave student ID to drop, it would just take this first line. So we need to identify that we want this whole column taken out. So that -1, I think it's -1 axis, or is it 1? I forget.
We have one that we
1.
used last time, so I don't know what one means.
Yeah, that makes it's 1 is saying this whole column.
Oh, that's right. If it's
Yeah.
like 0, it's row. If it's 1, it's column.
Yes. Yeah,
That's
yeah.
right.
But you can also make it a little more explicit and not have to deal with that, I found this out the other day by saying columns equals, and then pass in, oh gosh. Not that, straight brackets. Let's see, student, what is it called? Student ID. Right? Is that what we got? Or is it uppercase? Uppercase. Okay. So by doing columns equals, that's going to tell this we want the whole column, not, and we don't have to identify an axis then.
Oh, no way. Cool.
Yeah. So we'll drop that. Okay. Now we need to separate the features from our target. And let's see. So our features, we said we're going to be equal to all these, right? These are everything we want to pass in to make our guess on what grade they'll get. So we're going to take all these features minus this grade class. So let's go ahead and do our, let's see, data. And we're going to drop that column. What was it called? Grade class? Grade class, such a weird. Okay. So here we're dropping student ID, keeping all the rest of it here. Here we're taking all that's left in this minus that grade class because we're dropping grade class. So now our target is going to be that grade class, right? Because that's what we want to determine. That's what we want our output to be. So to do that, we can just target our data. Remember, don't pull it from features because we've dropped it. It's no longer there, but it's in data. So we're going to grab it from data. And that will be our target. Cool. All right, now next step. After we've broken them up into features and target, what do we need to do next? Anybody remember the next step?
Put the data in the training and test data.
Split it into training and test?
Yes.
Okay, yes, we're almost there. That is a good next step, but we're forgetting one thing in between there. If we look up here, what have we not used yet before we split?
Oh, we need to scale it.
Yes, exactly. Make sure to scale your data before you split it up. Otherwise, it might be a little wonky if you try to scale it after the split. So we're going to go ahead and define that scalar first. We're going to use the standard scalar that we've imported. And then we're going to scale the features. That's all we need to scale. Because we want to standardize, I mean, our target is 0 through 4. That's not going to change. We don't need to standardize that. But our features are going to be all over the place. We gotta lock them down into something a bit easier to work with. So let's do our scaled features is going to be that scalar dot fit transform. And I don't know about y'all, but I have bookmarked that working with data lecture with all the pre-processing stuff because it won't change very much. Might change on what you pass in, but good code snippets to have for sure. So here we scale it. We're going to use this fit transform to scale all of our features that we pulled out. Now, after we've scaled, this is where we're going to split our data. So I'm just going to copy and paste because it's going to be kind of the same thing every time. Well, no, I can't say that. It'll change. You can add some different parameters, but we're going to have the same layout, the X train, X test, Y train, Y test. Okay. X is our features. Y is our target / output. So here we use that train test split that we've imported, and we're going to pass in our scaled features as the X. Our target is going to be our Y. We're going to do our test size. It's going to be 20% of our data. And then random state 42. I still don't know what the random state. I gotta Google that some more. But I saw it somewhere and I'm gonna reproduce it. Gives us a good baseline, I guess. So this is going to split our data up. Are we good here? Can we finally start working on training our model yet? I've split my data. Am I ready to go?
So in my notes for the random state, I have it sets the seed for a random number generator, ensuring the split is reproducible, getting the same split every time you run your code. If that makes sense to you.
No, it doesn't. That's why I gotta Google it more. Like I read that too, and I'm like, oh, it just doesn't quite stick yet. I get it's a nice, it's a static point that we're doing this split from every time, but I don't know how that works. So I'd have to look into it more. But it makes sense to have it explicitly stated, so it's not just picking a place to split, I guess. I don't know. Okay, but back to this. Have we decided, can I now start training my model? Or what do I have to do next? We've brought it in, we've split our features and our target up, we've scaled it, we've passed it into these, I guess, are they arrays? To random train and test subsets. So what's like an array? What do I got to do with this? If my model, what does my model expect to take in as inputs?
The tensors, right?
Yes, thank you. We need to turn these into tensors. So here is where we're going to come across another difference between, let me just rerun this so we stop having that thing down there. Okay. Another difference between our binary model and our multi-class models is the way we convert these into tensors. So you'll see in the README that, I'm trying to find where it is here. There's a tab that says pre-process, or not a tab, a section that says pre-processing data. It says labels as long types. So our target can also be referred to as a label. It's the label of our classifications we're making. Maybe I should, now we'll leave it as target just so y'all can follow. But our labels need to be represented as integer types. And remember, when we did converting to tensors before, we turned them into these float. Now, looks like I got to import torch as well. Okay, so the binary model expects float types to be passed in. But with our multi-class, when we get to our, so with the X train and X test, we don't need to worry about that part. But when we come to the Y, the labels, which is our Y, label, target, all these words kind of make a link between them. These labels need to be a long type instead of an integer, because we're going to be using a different loss function than we did in the binary model. And the loss function that we're using now expects an integer, a solid long integer, instead of a floating point representation. Okay? So just try to remember in multi-class, first two are float, these are fine, but our labels, our Y, our target data needs to be long type. Okay? So that is the next difference that we pointed out. First one was our activation layer is using now the softmax. Next one is when we're pre-processing and getting our tensors together to pass in. Our Y train, Y test values have to be in long format. And now we're going to make our data sets Okay, so we're going to, again, this is all kind of rinse and repeat from previous lessons. You can find little code snippets. Oh, I don't know where this batch came from. Was this on a previous one? I am looking just to make sure I'm not teaching something new and crazy. Oh, you guys learned this earlier this week, I think, let me look and make sure. I'm gonna pop it on, and if you tell me this looks crazy or not. Let's see. Let me kick the dog out real fast. Sorry. Okay, so I think, let's see, looking back I'm looking on Monday's lecture. You created data sets and data loaders to help with training. So we're doing that here in our pre-processing because we're going to expect to train this model. So in Monday's class, created data sets, and I'm giving it a batch size, I guess. We probably don't have to do that, but we're going to. Oh, because instead of putting it in here, I see on your class on Monday, it's in here, but I just pulled it out and made it a separate variable. I don't have to do that. I'm just going to do it here. 32. Okay, so these data sets are part of what we need to do our training and testing of our model. Okay, so just taking that from Monday's class, nothing new or special. And it looks like it is pretty much word for word here. Yep. Verbatim copy from Monday. Okay, so let's go ahead and I'm just going to run this snippet to get everything in. And we are ready to roll. We are ready to start training our model now. Because we got all our data pre-processed, we put it into our tensors, made sure to have this one be long type instead of the float. And we're making our data sets that we're about to start training. Awesome. So now with our training, we are pretty much going to pull these from right out of the README. I'm going to put them down below the model. One thing to note that we will touch on later is because this model is going to put out, different values, a list of different probabilities, and we don't want that list, we just want one. You can see in the README that you can do something like this, which we will import. Where does batch features come from? Model batch features. Oh, that's what we're passing in. Sorry. That's going to be whatever we pass into the model. So this is going to be whatever tensor we decide to put into the model, and we're going to do this torch max outputs data in 1. So what this is doing is it's going to select the highest output or highest probability from this model. So torch max has 2 outputs. It returns 2 values. It returns, let's see if I hover over it, it will turn me. Returns the maximum value of all elements in the input tensor. Well, so it doesn't explicitly tell you, but it will return the maximum value, which they call the logit score. So the logit score is like a raw number, or the raw value. And then it also returns the index of the max value, which will be the predicted class, and that label. So we don't need the actual score. We just want like the raw logic score. We just want what it is, basically. We don't want to know a probability like 62%, it's 62% a 4.0 GPA. We just want to know it's 4.0 GPA. That's what it predicts. So we do this underscore to kind of forget that first part, and we just assign predicted then and print out our predicted score. But we're going to look a little more at that later. All you need to know is this max will select the highest probability classification and return that, or they call it labels, your highest probability label, and return that for you to see. So we will see that after we do all of our training, because I don't want to get any outputs yet. I need to train this model first. So again, just pulling this straight out of the README, because this should be kind of a review. However, if we look at this, there are a few things different between the training you learned on Monday and this training now. So one of the big differences with our multi-class is we're going to use this cross entropy loss as our loss function. Previously, you used something else. I think it was like BEC. I can't remember. I'm trying to look at it. I can't find it. Oh, there it is. BCE loss, which is binary cross entropy. So we can't use that because that's just for the binary models. We're going to use cross entropy loss because it can handle more complex data. And our optimizer, we're going to use Atom. That's still the same as before. The big difference is just this cross entropy loss. So again, we have how many number of epochs that we're going to run. And then we're going to just run it through 100 times. We're going to do, those forward stepping throughs, then the backward step, calculating the loss and adjustments of all the weights and everything that it's going to do to train that model for us. So I'm going to go ahead and run this. Let's make sure everything is. So I have inputs as my parameter. We're not going to say input. Wait, no, where is it? And train loader. Train loader is what we're going to be passing in. Let's make sure that that's what we have up here. It is train loader. Perfect. So we're going to pass in this data set for training. Let's go ahead and run it. So it should work in train loader. That looks interesting. Oh, I know something we didn't do before we ran this that will affect the performance of this model. Hang on, let me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so there's 14 of these, which would make sense here, but we dropped student ID. So we only have 13 features being passed into this model. So we have to actually edit this right here to be 13 in our first layer. It expects total 13 features in our model. So I'm going to restart this and let's run all. Okay, there's our model. Okay, I just want to make sure it's as accurate as it can be. So this is that training it's doing. It went all the way from 1 to 100 and went forwards and backwards, calculating all this loss, doing all that weight altering and emphasis for us. So we don't really have to worry about that. But now we're going to test it and we're going to see how accurate this is at predicting. So we'll build our evaluation loop now. So in here, we're going to import accuracy and we're going to change the task to multi-class. Okay. And our classes is how many potential, how many outputs are we weighing this between? If that's, I don't know how to explain. So our grade class is going to be between 0.0 and 4.0. So we could potentially have a 0.0, a 1.0, 2.0, 3.0, and 4.0. So that is 5 potential items it can be classified into. So that's where that number of classes comes in. We have 5 different classifications that this output could potentially be assigned to. So here we're going to do our testing, and we can see we just learned about this. It's going to select the maximum probability out of these 5 classes. It's going to take the highest probability label. That's the right way to say that. But if you want to think of targets still, it's kind of same thing. It's going to take the highest probability target and then update, accuracy update. I don't know what that means. I'd have to look into that. I wasn't prepared to talk about that. But it's going to go ahead and do that testing to see if it in fact equals what we think it's going to equal. So let's give that a run and see how good our model is. Oh, not bad. We're 77% accurate in identifying. And what did this take in? It took in our test loader, which was right up here, test loader. Awesome. So this model we built is actually 77% accurate in predicting a student's grade based on those parameters we put in. So technically that's all we were going to cover today, is kind of touching on how to build this model and the differences. Again, just to point out the major differences is number 1, in pre-processing, we use the long type or our tensors. And that is because when we come down to the loss, this cross entropy loss function expects integers, logits, not a float number. So if we pass it floats, it's going to mess up. It's not going to work very well. And then the next big difference is our activation layer. We're using softmax because it can handle this very complex learning here between a multi-classification. And then the other one we touched on a little bit ago is cross entropy loss. That's our loss function we're using. It differs from the binary loss function we used. And then the only other small difference is when we're dealing with our outputs, we have to select the maximum of it. So we get back just one value and not a list of all the probabilities. Any questions on this before I go into, I was curious and I wanted to pass in a student's features and get a grade thrown back at me to see if it works. So I was going to do that next, just as a fun little. But any other questions on the differences between our binary and our cross or our multi-classification one?
Yes, I have one. Where did you get the number of classes from?
Yes, good question. So that, where was it here? Down in our accuracy formula here, the number of classes is the number of classifications this grade class can fall into. So whatever your target is, let me get that picture up again of, because now we're just, let's see, open image and new tab. So remember this picture, instead of just getting one output, we're going to get several. So that number of classes is this. How many different outputs can our prediction go into? And with grade class, we want a prediction of a grade. We can see that we have zeros all to 4.0 is the potential grades we can get out. So if we count them, we can get 0.0, 1.0, 2.0, 3.0, or 4.0. So those are 5 different potential classes that our output can go into.
So it's not based on the number of, I guess well, I know because there's only one output that we see, but if that's the case, if I add 5.0, then that will make it 6 different outputs. So based on the it's based on the uniqueness of what we expect.
Yes, yes. So when you're looking at this, it is going to be all the potential outputs this could have. So like you said, if we added a 6.0, then we'd have six, or sorry, 5.0, we'd have six potential outputs for it to fall into.
So this is different than I'm seeing from the binary model where we know the output is just one.
Mhm.
Um, okay, so this isn't based on how we're defining the where will you go to the class where you're defining the layers and stuff?
Um, the
Here.
multi. Mhm.
So we got one, two, three, four. So it's not going to be based on the forward. So this is being based off the softmax and we self.ly. Oh, that's just a variable.
So it's going to be this, this is how much is output after each layer. So we can
Uh-huh.
see here, usually in the binary model, it would have been one, right? You end up with one. But here
Uh-huh.
we end up with five because we have five different predictions this model can make.
Okay. I'm okay. I'm seeing. So that last one is saying you have five different options. So we have to know what we expect in regards to options when we are defining these. Okay.
Yep, exactly. You are going to be in control of how you want to group the classifications. So with this, it's pretty easy because it's a small range. But if you were doing something like I said earlier about if you want to feed in a whole bunch of x-rays and get out, is it COVID, pneumonia, tuberculosis, or normal lung function? So then you'd have four categories, classes. So your final thing would be four instead. It's all based on how you want to define what your output should classify into.
Yeah, this part is interesting. It's somewhat it's a little confusing, but it's interesting because it's kind of like there's some manual stuff that we're doing to it when everything else we're automating, but this part just seems
Yep. So also another way you can think about it maybe is it's like a multiple choice question,
okay.
basically. And this number here you land on is how many of multiple choices you can guess from.
Okay, okay. I like
Yeah.
that. Okay. That
Yeah.
makes yeah. Okay.
Because I was thinking about that. I'm like, this could be a test question. What grade would Susie make on her test? And then it has five different multiple choice options. So
Okay.
that is how you determine the number of classes. So the classes slash class labels are what you're going to hear as this target. Um, so it might be easier for you to change it so it says class or label. That's the common phrasing for a multi-classification model output. Trying to see if there's anything else I may have forgotten in the README that we didn't touch on. But I think we touched on everything. Again, this is the cool AI. Like, yeah, we could say, is Susie going to get an A? Yes or no. But I'd much rather give this and just have it tell me what grade she's going to get. So now let's go ahead and test that. We're going to put in, let's see. I am going to take this out of my notes. I worked on this earlier today to kind of figure this out so you all can do this too for your challenge. But we're going to work on passing data into our model to get a prediction result. And it's going to be a little different than training because We've already trained it. We don't want to train it again. And I'll share this code after class too, or after lecture. So it's kind of, when we're passing in data to be evaluated in our model and produce our predictive output, it's going to seem a lot like we're pre-processing again, basically. We're going to get some raw data. We need to pre-process it before we pass it into our model to get a result. So we're going to kind of import a couple of the same things. We're not doing as in-depth pre-processing, but you may have to, depending on how your data is gathered and I lost the other word I was going to use. But depending on how that data looks, you might have to do extensive pre-processing, because we are going to pass in basically just a row of features. Okay, we want to just, I want to say, and this is going to look like not much here. I'm going to put it at the bottom. So I want to be able to pass this in. And each of these numbers, if we look back in our CSV, is going to equate to these columns. So she's 17 years old and a 1 for gender. So he or she, I don't know, whichever one, and then etc. So all these values equal those features. So you can do some stuff in your front end to kind of collect data from people and change it into values that a data set might expect, and then pass it through a model you build in the back end to get a prediction. Could be kind of cool. Anyways, so in order to do this, I'm going to build a function to call to do a prediction. So I'm going to predict grade. And in order to predict the grade, I'm going to need my model, because I don't have it just here. We instantiated a model earlier to train, but now I just kind of want to pull that model that's already trained and give it some information. We're going to need to scale this data, because we don't know if it fits the rest of the data that our model's been trained on. So we're going to scale it just to make sure that it's nothing crazy. And then we're going to pass in some new data. So now, first thing we need to do is, I guess, set to evaluation mode. I don't know why, I just saw that's what you have to do as the first step. I'm assuming because of the different, we do an evaluation here as well. Interesting. It's got to be a built-in function. Here we train it, and here we're doing evaluating it, or using it for evaluation. So first thing we're going to do is take our, whatever we pass in, we're going to make it into, we're going to standardize it to make sure all the data is where we want it to be. So we're going to take whatever data we pass in, new data, we're going to do that scalar. Good thing is we already, identified it up here in our pre-processing. We have our scalar set here. So we're still going to use standard scalar. So we're going to use that standard scalar, and we're going to transform our new data. So I just used transform here. Earlier we used fit transform. You can look at the differences between the two on your own time. Okay, so now we are going to, after we transform it into scale data, we're going to make them tensors, or make the data tensors, because right now this is not a tensor, this is an array. So we're going to take this array and transform it into a tensor. So we're going to have our input tensor. It's going to equal this. We do the torch. This is copying kind of the, how you've already passed data in to make tensors. So we're going to pass in new data. We're going to say the D type is that torch.float. We got to make it all the float 32. And then right now, if I pass this in this direction, this will not work because our model expects two-dimensional tensors, right? So if you look back in some of our previous lectures, we did this thing where we reshaped our tensors in order to be able to plug into our models. So we're going to do the same thing here because right now it's just flat. It's one-dimensional. We need it to be two-dimensional. So here we're going to do that view. So we can go ahead and return a new tensor in a different shape to be able to pass into this. And this is so I can pass in a single input. If you had like multiple, you probably wouldn't have to do this, but I just have a single input here. And we're going to reshape it to doing this 1, -1. Now, does anybody know what that 1, -1 does for the reshaping?
I think it's like one array of whatever the length of the data is.
Exactly, Danielle. Woo! Gold star. That is perfect. The first number here is the batch size that you're passing in. So we're just passing in one student at a time. And then the second one here, a -1, will automatically infer the length of this array. So again, if you have lots of students you're passing it, you can do this one -1 because it'll automatically infer the number of students you're passing in the batch. But we only have one single input, and we want it to be the entirety of this array. We want to make it two-dimensional. I'm impressed. That was good. I didn't know what that was even until I looked into it again more today. And I'm pretty sure no, you all must have learned that in the tensor class. Okay, so we have our input tensor. Now we can pass that into our model to make a prediction. So we're going to do this with Torch. No grid. So we can see we did that up here too. We're going to, our output is going to be equal to our model and our input tensor. And that does the forward pass through our model. We have to, since we don't want a whole bunch of probabilities with our output, we're going to have to do that thing here. And we did up above where we're just taking the predicted class or predicted. And we're going to take that from this output because we don't want everything. We just want what is, call it output. We just want the most likely grade she is going to receive. And then we're going to return. Oh my gosh. We're going to return predicted class or predicted, sorry, we're going to return predicted item. So that right here, I looked this up, it returns this as a number. So this is going to return this tensor because remember when we ran before with our models, it returns like tensors and other stuff with it and everything. This is going to convert that to just an integer instead of that tensor. And I'll share this with y'all. I think you're going to go more into this on Saturday, but if not, this is kind of a little good preview of how to work with a model. Okay, so we want to pass this new student in to get a predicted grade. So we're going to say predicted grade is going to equal, we're going to call predict grade function here and pass in our new, we'll pass in model. We've identified that above previously. We've got model here. So we're going to pass in the model we've been working with. And we're going to pass in our scalar because that is also identified above as our standard scalar. And then our new student is going to be the data that we're passing in. And we're going to print. I made it all pretty here, so I'm gonna I did an F string to see predict. I like it called predicted grade. Okay, so if all is well, if everything's good, when I pass this in, this should return back to me what her grade should be. So let's see. Oh, what did I get? Value error 1D. I thought I did a view. Okay, let's try something different for this. I came across this earlier too. Instead of doing reshaping here with the tensor, we're going to reshape earlier and see if that helps. So before I even scale it, we're going to reshape. And this is where I use that numpy. So I thought it would work the other way. I guess not. I'm still learning this. New data is going to be a numpy array. We're going to pass in that new data. And what we're going to do is we're going to reshape. And again, we're going to do the shape we talked about before. We're passing in 1 and we're taking everything. Let's see. So this should work now. We're reshaping here. And then we're going to transform, we're going to scale it with our standardized scaler. And then we're going to pass it in. And since it's already reshaped into a 2-dimensional, we don't have to do a view here to do anything to that. Okay, let's try it again. All right. This warning I don't really care about. It says X does not have valid feature names, which is fine. I'll explain this in a bit, but look, sure, predicted grade class is 2. So guessing a 2.0. Or it could be class 2, which is 0, 1, 2. Oh, her predicted grade class is going to be, that's the index of the class. So we have, let's see, where can I write this? This is going to be, our output is anywhere, it's 0. Oh no, it isn't the index. Yeah, it is. No, I'll have to look into that more. But our output is going to be like that, which will equal our classes, which were 0, 0.0, 1.0, 2.0, 3.0. Y'all can play around more with this to see if it gives the actual value of that class or if it just gives you the index or location of that class. That I do not know. But that is the predicted grade for this student based on these values here that I passed into the model. Okay, briefly, this is just saying that, so up above we passed in feature names in our standard scaler, but down here, when we pull this in, this doesn't have any names on the features. This is just numbers. So this is just saying that down here, we don't have names to associate with these features, but it's fine because I knew what to do with it already. You could fix it to ignore that, but this works. It's just a warning. It's not an error. Any questions on this little preview? While y'all are working, I'll probably do some more digging in here. I assumed it was the actual value of the class, but since it doesn't say 2.0, I'm unsure. It might just be the, index of it in the classification list. We'll see. Questions before I stop recording? All right, well, let me stop recording and we'll go over challenge for the day.